Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi, students. So we continue our discussion with alternating circuits. As you know, alternating circuits ties alternating current is the effect of generators which generate alternating current. It comes about because of a time varying magnetic field. Now, the time varying magnetic field basically comes because of the flux, right? The flux, like, so you have two magnets, and in the middle, you have this rotating coil, right? This rotating coil has induced current, and that induced current varies because the area occupied by that flux is changing. Because the area is changing, you have, let's say, if you have a constant b, the b dot a changes, right? And so as a result, you have n, like when you do like the phi is ba cos omega t, right? Why is it cos omega t? B dot a, right? So ba cos omega t, and you take that derivative, you have and you have n turns, right? So you have a n times a coil, and then that is rotating, right? So now, when that coil rotates, you end up with a d phi by dt. D phi by dt is sine, but then you also have the omega. So NBA omega, right? NBA omega is your times root 2, well, times 1 by root 2 will be your average EMF. Okay. So that drives your, that is the voltage, right? That drives the power the circuit can generate. So if you have V times I, it will produce corresponding power. Okay. So now you have a sinusoidal voltage. If you had just a resistor, the resistor will be the current through the resistor will be in band, in sync with the voltage. So if this is V sine omega t, the current will be I sine omega, will be Vm by R sine omega t. This is sine, this is also sine. So we say that these two are in phase. So if you have a single resistance circuit, they stay in phase. Okay. So if this is V, this will be I, right? This is a sign, that's also a sign. It's just a ratio, right? So and they have what is called a phasor diagram, which kind of tells you that as time goes by, right? As time goes by, what happens? The phase uh, stays together, right? The I and the V have the same phase. The only the difference is the value, right? So one is longer, the other is shorter, but they rotate in sync, right? You see, they have the same omega, and they have the same phase as well. Both omega and the phase are same. So now if you wanted to calculate the average power, it is just 1 by t. So over one cycle, what is the average power? 1 by t f of t, right? Now power is v times I, right? So in this case, right, v times I is always positive, right? V times I will be sine square, right? And sine square is always positive, so it'll be like this, right? So so as a result, you can then calculate the power, right? So so sine square omega t will be, can be written as 1 minus cos 2 omega t by 2, and then when you do the integral, it will become t minus cos 2 omega t will be sine 2 omega t, right? And then you can write the put in the values for the limits, and you will find the corresponding power. Right? The average power is I RMS square R, and I RMS is I times 1 by root 2. Okay, V RMS is V times 1 by root 2. Okay, so 1 by root 2 is, so sine, what is the average for sine? For sine over one cycle, it is 1 by, the RMS for sine is 1 by 1 by root 2, right? Therefore, you have Vrms is V times 1 by root 2, and Irms is I times 1 by root 2. And therefore, the P average is I square RMS times R. So it will be I max times root 2 by root 2, right? So it will become I max square R by 2. Okay? P times I, right? Therefore, so now let's look at this one. So, alternating current is applied to a pure resistive load of 50. The time taken for the current to rise from half of the peak value to the peak value. And half of the peak value is what? Peak value is 220, right? What is the half of the peak value? 110. So what is the sine? So zero point 0.5 equals sine 100 pi t by 2, right? So when is sine theta half, right? Sine 30 is half, right? So, or pi by 6. So 100 pi t naught is pi by 6. So at what time does it become 1? That is when 100 pi t naught equals pi by 2. So from pi by 6 to pi by 2, you therefore end up with 1 by 600 to 1 by 200. Therefore, you subtract 1 by 600 and from 1 by 200. So 1 by 200 is 0.005, 1 by 600 is 0.016, therefore roughly 3.3 seconds. So this is a very simple question. If you understand what's going on, calculate the time taken for the current to rise half of the peak value to the peak value. What is the peak value here? Im. What is the half the peak value? Im by 2. It is not the RMS value. RMS value is Im by root 2. Okay. So now let's say you have just an inductor. Now, an inductor, what is the equation for an inductor, right? The voltage across an inductor is L di by dt. So EMF V sine omega t equals L di by dt. So if you solve that differential equation, you will end up with a value. Now, what it typically does is, if the the capacitance will lead, the inductance will have a phase lag. Capacitance will lead the voltage. The inductance will lag behind the voltage by pi by 2. And the amplitude will be Vm by L omega. Previously you had Vm by L, right? Now you have a extra omega, because however fast that's how what happens with the derivative. There is a omega from the omega t, right? So when you differentiate sine omega t, you have cos omega t. But then you also have to differentiate omega t, and that will then produce omega, an extra omega, right? Therefore, that's how you end up with that Vm by L omega, right? So the current is Vm by L. Okay. So Vm by L omega sine omega t minus pi by 2. Okay. So now what you see is the voltage is here, the current will be 90 degrees behind. Okay, so AC source with inductance, the current and the phasor diagram. So the current will lag the voltage by 90 degrees. The opposite is true for a capacitive circuit. Okay, now what can be said about the power, the instantaneous power that is taken up by the by a capacitive by a inductive circuit is always zero. Okay, so the inductive power is always zero. Okay, so why is that? Because you have sine 2 omega t. One is sine omega t, the other is phase lag, so it is cos omega t. So sine omega t times cos omega t is sine 2 omega t. It's not sine square, right? Sine 2 omega t. So that will be another sine curve with twice the frequency, right? So that is going to go so over one period it is going to have zero as the V times I. Okay, so same is true about the capacitance. Okay, so the energy which is absorbed by the inductor is then given back to the system. Okay, so vi, the average vi will be 0. Now, so the only in any circuit, only the loads which are resistive will absorb power. Okay, so now let's say you have, so we then introduce this term called impedance. Okay, so the impedance, right? So when we talk about the impedance, it will have both a real component and an imaginary component. The real component will be R, the resistive part. Imaginary component will be a combination of X. Like, so you can look at this, right? You look at this value, right? L, like you can think of this as a resistor, right? If you leave out the phase lag, the corresponding, if you did an RMS of this, the corresponding value there is a, can be thought of as a resistance. Vm by R sine omega t, right? Here it is Vm by Lw. So we say that the reactance is omega L. Okay, reactance is imaginary. Okay, so now you introduce something called impedance, which is both, includes both the resistance and the reactance. Impedance is a combination of the resistance and the reactance. It is a complex number. The resistance is a real number, is the real component. The reactance is the imaginary component. Now, for a capacitor, for a inductor, the reactance is omega times L. For a capacitor, the reactance will be 1 by omega C. Okay, so if you have both, then you'll have omega L minus 1 by omega C, because one leads and the other lags. Okay, so it will be tricky because of that, and we'll look at how these things work. So if you had a LC circuit, okay, so you can in an LC circuit, so let's look at this example, right? So here you have the I and we have the V, and then the I is out of phase, and you have the energy over a cycle as 0. So now what is the IRMS? If you have 48 millihenry, 240 volts, the IRMS is 240 by 48 times omega is what? 2 pi f. 2 pi times 50, right? And 48 times 2 pi 50 will give you the XL. So 240 is the voltage. 240 by omega L is 16 amperes. That is your IRMS, right? Or are we missing something here? What are we missing here? Right? We are missing actually a root 2, right? This is the peak. Vm by Lw is the peak, right? So if you wanted the IRMS, you have to divide this. This will be Im. You need to divide by root 2, right? 16 divided by root 2, or 240 divided by 16 root 2. Okay. So now if you have an alternating current, right? And you have just a resistance, current is in phase. Now if you add both a resistance and a inductance, what happens? It will be, the inductance circuit is 90 degrees out of phase, but if you had both, then you will have a correspondingly different solution, right? So now a resistive circuit in which RMS value of the current is 5 amperes. What is the value of current 1 by 400 after it becomes 0, right? So the Im sine omega t, right? So you have Im as 5 times root 2. If this is, if IRMS is 5, then Im is 5 root 2. So the equation is 5 root 2 times sine, and the frequency is 50 hertz, 2 pi f times, so 100 times pi t, right? Therefore, now you can look at I equals 5 root 2 times 100. Now, after a time t of 1 by 400, what is the corresponding value? You will have a result. Okay. Now, similarly, if the voltage is in omega equals 400 rad is in 10 Henry inductor, at the instant when the voltage is minus 12.5, magnitude is increasing, what is the current? Current will be 6 Vm by omega L 6.25, right? So now let's take a look at this one. V of t equals minus 12.5 and omega t equals 7 pi by 6 and 11 pi by 6. Magnitude is increasing at omega 7 pi by 8, right? So what you should do with these questions is you must understand what's happening in the sine curve of either the current or the voltage. Now, if you have a inductance, the inductance is going to lag. So you put a minus pi by 2 there. If you have both, we will be looking at how to deal with that. Okay. So now in a purely capacitive circuit, it will lead. The reactance is 1 by omega c, but then it will be omega t plus pi by 2, you know. So when we look at the you will have r plus j omega l, and in this case r plus r minus j by omega c. J is just square root of minus 1, the imaginary number like I. Okay, square root of minus 1. So r plus, if you had both a resistor and a capacitor, you will have r plus r minus j by omega c. Okay, where omega c is the corresponding xc. Okay, so that will be the what we call as the impedance, which is a complex number. So if the voltage is here, the current will be there. Okay, so that is a capacitive circuit, right? So now what happens is in a capacitive circuit is that half the cycle the capacitance will be charging. Okay, so if you look at this, it is pi ahead, pi by 2 ahead. So when the voltage is zero, the current will be there, right? But at the peak, the current will go to zero. Why is that? 1 by c integral I dt. Okay, is the voltage, right? So at this point, the voltage peaks. And when the voltage peaks, the current is zero. C dV by dt. What is the current in a capacitor? C dV by dt. Q equals CV. Therefore, dQ by dt equals C dV by dt. Okay, Q equals CV. Remember that. So C dV by dt. So when dV by dt goes to zero, which will happen at the peak, right? This will go to correspondingly zero as well, right? So the derivative of the voltage gives you the current curve. Okay, C dV by dt is the current. I equals C dV by dt. Therefore, and it leads, right? If this is sine theta, that is cos theta. Derivative of sine theta is cos theta. C dV by dt. So and therefore you have the corresponding equations. Okay, so here's an example. At the instance when the v of t is minus 12.5 and is increasing in magnitude, what is the current? If v of t is increasing in magnitude from a negative number, then it is becoming more negative, right? So the current will be negative, right? So what is the value of the current? Value of the current, what is the xc? Xc is 1 by omega c. It is 1 by 400 times omega is 400, right? And the this the capacity c is 10 to the power of minus 5. So it's 10 microfarads, right? 10 times 10 to the power of minus 6, therefore 10 to the power of minus 5. So 1 by 400 times 10 to the power of minus 5. So 2.5 ohms. That is the reactance. So the Im will be Vm by Xc. Vm is 25 sine omega, right? 25. So 25 by 250. So that will be your Im, right? So you write Im sine omega t plus pi by 2. Okay. Therefore, so zero point 0.1 times sine omega pi by 2. So at a particular t, you can calculate what is the current. Okay. So what is the V? V is 25 sine omega t. When is V? So you say 25 sine omega t equals minus 12.5. So then sine omega t is, so omega t equals negative half. So it is, so what is the time at which it is negative half, right? So if you have sine curve, will be at a point 7 pi by 6 plus pi by 2. So at what point is it negative 12 and a half? It is at 7 pi by 6, right? So it is pi plus pi by 6, pi plus pi by 6, right? So that is when it is negative half, right? When is sine omega negative? In the third quadrant. All sine, tan, cos, right? So um, you got to understand how to do sine and cos, and you got to understand how to set the time, and then understand the sine curve, and then the taking the derivative of the sine curve. Okay, and then now impedance is another way of understanding, is a way of doing sine and cos, okay, by almost like it is a resistor. Okay, and so you treat impedance, which is real part resistance plus j times imaginary part reactance. Okay, so understand how that's the dynamic behind that. So why is there this omega there? This omega is there because you're taking a derivative. Okay, therefore that's how you end up with that c dv by dt. Okay, so so now if you have two capacitance in series, it is 1 by c1 plus 1 by c2 equals 1 by c equivalent, right? So what will be the effective c? The effective c is going to go down, right? And therefore you have 1 by omega c1 plus 1 by omega c2, right? And therefore you can take the omega 1 out, and then you can do 1 by omega times 1 by c equivalent. And 1 by c equivalent is 1 by 10 plus 1 by 20, right? And 1 by 10 plus 1 by 20 is 3 by 20, right? So 3 by 20 times 1 by omega, right? Therefore your xc is correspondingly that. Okay, so 250 plus 125, 1 by omega c is 250, this, right? So 250 plus 125 is 375, right? Therefore you have um, uh, your xc goes up because it's additive, right? But the net capacitance goes down. Okay, so you just do an add of these two, therefore you end up with 375 ohms. So 25 divided by 375 will give you the Im. So you write so the current, and therefore once you know the current through the circuit, you can then find the V across each of them. The V across each of them is I times xc1, and the V across the second one is also I times xc2. Okay, think of xc as just like a resistor, only it has an imaginary component. Just think of it that way. Remember, eventually we are going to write it as a Impedance is just a the it is like a resistance. Only thing, also has a complex part. Okay, so impedance is a all encompassing situation where you can include capacitance, resistance, and inductance in a circuit, and you treat all of them as though they are all resistances. Okay, so the impedance, or so for a what is that, for a inductor, it is just j omega l. For a capacitor, it is 1 by j omega c, or negative j by omega c. Okay, so remember that, and remember it well. So if you have purely resistive load, current is in phase. If you have a purely inductive load, current lags. If you have purely capacitive load, current leads. Okay, if you have combinations, you will have corresponding mix of results. Okay, so if you have an LCR circuit, okay, then you have a V and I, and then there is a some phase shift. You never have anything which is purely inductive or purely capacitive. There is always resistance. So you have to correspondingly account for it. Now, um, one way is to use this cos theta plus I sine theta is equal to e to the power of I theta, right? De Moivre's theorem, right? What is De Moivre's theorem? E to the power of I theta equals cos theta plus I sine theta. So you can write the voltage in these circuits to be Vm times e to the power of I omega t, and that is another way to look at it. Okay, and but then see, my suggestion is just understand the impedance. Impedance is a complex number. Okay, and just work with that, and remember the impedance. So what is so this is the slide that actually introduces the impedance. So if you had a series L, C, and R, the R is the real part, the L and C will have purely imaginary parts. So the impedance of a inductor is omega times L, and the impedance of a capacitor is minus 1 by omega C, right? Therefore, you have a real part which is R, and an imaginary part which is XL minus XC, or omega L minus 1 by omega C, right? Therefore, the Z has a absolute value of the complex number is a square plus a plus ib. What is the absolute value? A square, square root of a square plus b square. What is the magnitude of complex number? A square plus b square, square root of a square plus b square. What is the phase? Tan inverse of the imaginary part divided by the real part. So what is the phase? It is the tan inverse of the imaginary part divided by the real part. So you will have an angle, a phase angle, which is set by evaluating the tan inverse of the imaginary part divided by the real part. So what is the power IRMS? Im square R by 2. How do you end up by 2? Because it is IRMS by root 2 for I, right? So, and it is IRMS square R. Therefore, 1 by root 2 times 1 by root 2 is 1 by 2. Okay, so the in an LCR series circuit, you therefore have a phi which is proportionate. If you have a more inductive circuit, it will lag. The net effect will be a lag. If you have a slightly more capacitive circuit, net effect will be a lead. Okay, the phi will then become slightly positive. Okay, so tan inverse of the reactance divided by the resistance will give you the phi. Okay, so this is the LCR series circuit. You can have LCR parallel circuits, etc., etc. Okay, so the student is advised to understand and memorize this for LCR series. Understand and memorize this particular diagram, this particular slide. In case you want to read about this, this is from Wikipedia. Okay, Wikipedia teaches you about the ideas that are there in this set of slides. Okay? Now, based on how a circuit is set up, right? The voltage across the resistor, right, will vary based on, there is a window where the inductor and the capacitor cancel each other out, and that window is when the voltage across the resistor is maximum. Okay, that the point at which it goes to zero, the voltage across the resistor will be the highest, because omega L will completely cancel out omega C. If omega L minus omega C goes to zero, then your tan phi will also go to zero. And on top of that, it will be a purely resistive circuit because it's in resonance. Okay, that is called a resonance point. So and that point happens when omega naught equals 1 by square root of LC. So this numerator here goes to 0. Therefore, you have omega L equals 1 by omega C. Therefore, omega square equals 1 by LC. So omega equals 1 by square root of LC. Okay, and your alpha becomes R by 12. Okay, so my point in teaching this at a more slower pace is to because this material is not that straightforward. Okay, so then your voltage across the resistor in the LCR is band pass. What does band pass mean? Band pass means there is the voltage is maximum. It will be something like this. Low voltage is the voltage across the resistor will be small, but there'll be at that omega naught equals 1 by root LC, it will be maximum, and then it will decay again. So that's what they mean by band pass. Now, an LR circuit is low pass. When we say, we are always measuring the voltage across the resistor, right? In an LR circuit, at low frequencies, there's a lot of voltage across the resistor. In a RC circuit at very high frequency, if the voltage is moving very fast, the capacitor will be a short, and therefore all the voltage will be across the capacitor. At low frequencies, the inductor is a short. High frequencies, the capacitor is a short. What does short mean? There's no voltage across the element. And you can easily understand that, right? Q equals CV. When you take the derivative, dq by dt equals C dV by dt uh, uh, when the current is when your um, um, RC is very high, right? Um, when the voltage is very high, right? You tend to have the resistor having the most voltage. Okay, so if the voltage is has a very low frequency, then the and you have an LR circuit, the LR circuit will have the most voltage across the resistor. That's what we mean by low pass. Okay, so these are what are called filters. A filter, what does it do? Based on the incoming frequency, the voltage across the resisting element will vary. So what does that mean, right? So um, various circuits are set up to be tuned to frequency. So that's what this is all about. They produce higher voltages and lower voltages based on the frequency, and these circuits are tuned to do well based on a particular frequency. Okay? Electronics is, of course, a very clever science. because they do a lot with these circuits in order to make these circuits behave in certain ways. Eventually you will, once you bring in the transistor, they will synthesize these circuits using what are called active elements. We will worry about that when when you guys get past this and then learn the same thing in a circuits course. But till then, we want you to learn this well and take things forward. Okay. So with that, I'm going to break for today. We will continue our discussion next time. Okay. So with that, I'm going to stop, and we can discuss this again next time. All right. Thank you.